Hi all, this is Mr. Yeager for Honors Chemistry. Today we're looking at electron configuration and orbital diagrams. So we're finally to the part where we are looking at the actual arrangement of the electrons in every single energy level and breaking that down to a very big detail. All right, so here we go. Okay, so at this point we already know electrons are in energy levels. They can move between these energy levels, and light is released when they move from a higher to lower energy level. So that's what we saw with the atomic emission spectra. Okay, so what we're looking at next is we want a clear, regular pattern method of how to illustrate where each electron actually is. Okay, so why is this kind of important? Okay, knowing where the electrons are in the atom basically helps explain their chemical properties. Okay, there it goes, chemical properties spinning. All right, so like we kind of talked about with valence electrons, the number of valence electrons in an atom will help us define how it basically reacts, because it forms particular ions and therefore it has particular properties based on that arrangement. Okay, so that's the big why behind it. So what are we looking at here? Okay, Bohr's model of the atom put electrons into what we call principal energy levels. I know I've been saying energy levels, but they're actually called principal energy levels. Okay, again, you have this diagram to the right here showing you a gold atom. I chose this one because it has a lot of energy levels. Okay, but we count from the inside out all the energy levels. So the one on the inside is n equals 1, n equals 2 would be the next, n equals 3, n equals 4, n equals 5, and n equals 6. Okay, we have the 6th energy level right there. All right, with gold, all right, you have those 6 separate energy levels. Each of them, the dots all represent electrons. There's a certain number of electrons that need to be filled in before we keep moving out to the farther and farther energy levels. Okay, but we always go from the inside out, and again, they're called principal energy levels with the symbol N for denoting that. Okay, and so that's basically what we just said here. Each ring represents an energy level. Okay, there are actually 7 total energy levels. Okay, there's 7 total energy levels, so this N number can go from 1 to 7. All right. We'll look at it, I mean, you can already look at it now. If you look at the periodic table, there are 7 rows, all right? So the periodic table is created with the energy levels in mind, showing how the electrons keep on adding to a new energy level every single row we go down. We'll get in more detail about that in the periodic table lecture, okay? But that's what we have. So there's 7 energy levels that these electrons go in. The energy levels are the broadest way we can say where the electron is. So that would be like, hey, you are in this neighborhood, okay, at this time, okay? So after the principal energy levels, inside each principal energy level is what's called an energy sublevel, okay? And so there are a certain number of sublevels in each energy level based on what what principal energy level you're on. I know it's all these levels, energy levels and all that. So the number of sublevels will equal whatever the principal energy level number is at that time. So for example, if you're in the 2nd principal energy level, n equals 2, there are 2 sublevels. We will see that we write this as 2s and 2p, okay? Not to go too crazy about it, and I'm going to show more of the letters on the next slide. I think it's on the next slide. Let me see real fast here. Okay, yep. So again, the number being the energy level and the letter being the sublevel, okay? You're going to see we name the different sublevels with a letter, okay? And so the diagram over here is actually showing you all the different types of energy levels that basically exist. You do not need to remember any of these shapes or anything, but what it comes down to is basically these sublevels is almost like a probability area of where that electron is going to be located. Because again, the electrons are still repelling each other, and as you keep on jamming more electrons into the atom, there's going to be a repulsion factor. So they create these different shapes that end up fitting the atom well, okay? So for example, this one up here, this is probably the easiest to understand. This is the S sublevel. It's basically, S sublevel. And it's basically a spherical shape, okay? again, a three-dimensional spherical shape. When you get to the p sublevel, there's actually three different, what we're going to call orbitals in this p sublevel, and again, they're aligned based on the different axes. And you can see they do definitely get more complicated in their arrangement as they go down. You do not need to remember that diagram. I just wanted to share it with you of why and how these electrons actually are going around the atom. Okay? So there are four sublevels, S, P, D, and F. All right? Okay. So let's keep going for now because you're like, S, P, D, F, why is that? Okay? So each type of sublevel holds a different but set number of what we call orbitals. So there's principal energy levels, sublevels, and now orbitals. Okay? The orbital, this is where you can actually find the electrons now. All right? Is somewhere within the orbital. So again, if I kind of do a little bit of like a analogy, all right? I'm going to kind of actually narrow it down a little bit. The principal energy level would be like a house. The sublevel would be the floor. So if we're saying, where are you? We could say, well, you're at least in the house. Then what floor are you on? Then the orbital is the room that you're in. And then the electron is you, the person itself, okay? So again, we are getting more specified of exactly where that electron is. Not just, hey, they're in that house, but where are they in that house, et cetera, okay? So orbitals, this is where the electrons actually are, and we're going to learn you can either have one or two electrons in the orbital, okay? One or two, and that's it. So that does lead us to a couple of formulas we're going to see in a minute, but for now, this is what we need to realize, okay? Each sublevel, as we mentioned, holds a different but set number of orbitals. The S sublevel, which is going to be the lowest energy sublevel, has one orbital. P has 3, D has 5, and F has 7. So it is something, again, you will get used to. It's 1, 3, 5, 7. S, P, D, F. 1, 3, 5, 7. All right? And so the idea is each of these orbitals can hold up to 2 electrons. All right? So I'm already going to point it out now. If I only have one orbital, it can hold up to 2 electrons. So the S sublevel can hold 2 electrons. The P sublevel has 3 rooms, 3 orbitals. So 3 times 2 is 6 electrons. So the P sublevel can hold 6. D sublevel can hold 10 electrons, and F sublevel can hold 14 electrons. Again, multiplying each by 2. All right? So again, a lot to kind of put your head around because it's probably very new and seems very random, but there is a pattern to it once we figure it out. Okay, in terms of once you have these rules down, this is always what the pattern's going to be. Okay, and it won't change. There's no real exceptions with it that we will go over. I say that there are exceptions, but we will not go over that specifically. Okay, so if we want to try to finally get this all together, okay, you have principal energy levels, sublevels, orbitals, electrons. Okay, as I'm going down, I'm getting more specific, I'm getting smaller, okay, is what I'm looking at there. So there are a couple things that I might ask you about these. I might ask you how many orbitals there are in the P sublevel. You should just know that it's 3, etc. Okay, but there's a couple, so these are the things I might ask. If I say I want to know how many sublevels there are in a principal energy level, they're equal to each other. Okay. So third principal energy level, third 3 sublevels. Okay? Orbitals can hold up to 2 electrons. So therefore, I can figure out the number of electrons in an energy level by doing the formula 2n squared, where I square n first, the principal energy level, and then I multiply it by 2, and that'll give me the number of electrons. Okay? So that leads us to a little bit. So here we go. I already wrote this on the last page. Okay? Good. All right, so let's practice some of this counting. Okay, determine the number of sublevels. If I'm in n equals 2, sublevels is equal to n, so that means I have 2 sublevels. And in the end, I'm going to write down which ones we have just so you see them and you kind of get used to that. We always start with the same sublevels because you're going to hear one of the rules is we always start at the lowest energy first. Okay, n equals 5, that's going to have 5 sublevels. Now you might be going, wait a minute, what the heck is G? There is actually another sublevel called G, we will never reach it, but it's the idea that you could reach another energy level, an energy sublevel within that larger atom. It's just we usually aren't going to fill it when it's at ground state. Okay, remember what ground state is. N equals 4 sublevels, S, P, D, F. How about number of electrons? If I give you the 3p, okay, and again, we'll get used to what this means. So I'm in the third energy level, P sublevel. So I'm being pretty specific here. If I'm in P, P has 3 orbitals. 3 times 2 is 6 electrons. And that's because, not because it's the 3 right here, it's P is 3 orbitals. 5s, again being specific, I go to the smaller, more specific area, which is the sublevel S. S has 1 orbital. 1 orbital times 2 is 2 electrons. If I'm in N equals 4, now I use that formula 2n squared. Okay? If I do 2n squared, I'm going to do 2 times 4 squared, 2 times 16. This is going to be 32 electrons. Okay? 32 electrons. So that's how we can solve for it. If I give you something more specific, like I just said, with the sublevel, okay, like this gives you the energy level, the principal energy level, and then the sublevel, I use the sublevel to tell me the answer because I'm being more specific. Okay? Oh, I have one more. N equals 2. 2 times 2 squared. 2 squared is 4 times 2 is 8. Okay? All right. So this now leads us to, let's actually write out the electron configuration. Okay? So the electron configuration will tell me what energy level the electron is in. It'll show me what sublevel the electron is in, and it'll show me how many electrons are in that sublevel. So I need a number for the principal energy level, a letter for the sublevel, and then a way to show the electrons. So what I have is something like this. This is just showing you a portion of a electron configuration, 2p4. So the big 2, that's your energy level. The p is the sublevel. And then the 4 that's written like an exponent, okay, is the number of electrons. So what I'm saying here is that I'm in the second energy level. In the p sublevel, there are 4 electrons currently located in the p sublevel. Okay? And so we're going to see that we have to be able to add up all the electrons because we're going to do this with neutral atoms. And if you recall, with neutral atoms, and we're also going to do ground state atoms, okay? That means all the electrons are where they should be. There's none jumping up higher or anything like that. We will see that, again, the number of electrons should equal the number of protons, which is the atomic number. So we're going to use the atomic number to help us out here to figure out the electron configuration on it. Okay, so that's what we're going to use with the periodic table. All right. But the first rule, there's 3 electron configuration orbital diagram rules. And the only one I need to introduce right now is what's called Offball Principle. It's actually pronounced off-ball. Okay, so it should almost be like O-F-F-B-A-L-L. Offball Principle. Electrons will always enter the lowest energy level first. Okay, we always enter the lowest energy level first. All right, even when you're at a much higher element farther down on the periodic table, you will see that we always start in 1s, and then it's going to follow by 2s, and there will be a pattern that develops. Okay, this diagram right here, I'll try to quickly come back to it after I go through it. I think the best way to learn this is off the periodic table, but this little diagram here can help you remember what comes next as well. So we'll come back to that. So here we go. Okay. So on the periodic table will tell me how to do all of the electron configurations. So this does take a bit. Okay. So basically what you can see here already, kind of drawn out, is there's 4 different blocks on the periodic table. There is the S block. The S block is the first 2 columns. You can see they're one color. Okay. So electrons added in these two columns over here are going to be in the S sublevel. We do have the one exception with helium over here. In this case, we can almost think it's right here, right next to hydrogen. But again, it's on the other side. But this is one row at the top. Okay. Then, from there, we have what's called the P block. The P block has 1, 2, 3, 4, 5, 6 columns in it. And again, we're ignoring helium. Down here, we're going to learn these are called the transition metals. This is the D block. Okay? And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots in the D block. And then down at the bottom here, this is our F block. So if you end up in the F block, your last electron is going to land in one of the F sublevels in the end. All right? So we have these 4 different blocks. And again, that can help us say, I know I need to end with something with P. I know I need to end with something with D. If I'm saying find the electron configuration of MO, my final part of it will be 4D something. And again, we'll go over that in a second. Okay? This might be something you do. You get your periodic table out right now, and you basically write what I'm going to write on here. Okay? It would really help out. Because just you're not going to really understand it until you start using it a lot, and then you'll get used to it. So, what we're going to do is, basically above each column, we're going to write an electron number, or configuration number, I'm going to call it. Okay? So this column, the first column right here, they're always going to be finished with S1. Okay? We'll get through this, I'll explain all of it in a moment. S2 is the second column. I'm going to skip over here. Helium is also S2. If I go down to the P block now, this will be P1, P2, P3, P4, P5, and then a neon P6. So P6 is from neon on down. The D block, D1, D2, D3, D4, D5, D6, D7, D8, D9, and D10. Okay? And then down at the bottom, we actually have to go from F1, I'm not going to write all these out, to F14. Okay? So 1, 2, 3, 4, 5, 6, 7. I'll put F7 right there. 1, 2, 3, 4, 5, 6, 7. Okay? And it goes all the way up. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? All right. What I'm trying to point out there is this is we're going to use the row number to figure out what the principal energy level is at the end of the configuration. And then we're going to use kind of these column numbers I just wrote to figure out what would be the ending part of the configuration. So again, going back to my MO example, there's a lot more to it, but the idea here is, and I know this is a little bit weird, I should probably use a different example. Let's start over here. Let's start with Na. If I say, I want to know the electron configuration for Na, there's all sorts of stuff I have to go through, but it will end at 3S1. Like that's going to be the last thing you write on the electron configuration. That's all I'm trying to point out at this time. Okay? But again, the row number is basically the row number is the energy level number. Okay? So let's start off with some of the ones at the top. Let's actually just start off with hydrogen. Okay? We're going to kind of do a bunch of these. With hydrogen, hydrogen has 1 electron. How do I know? The atomic number is 1. We're talking about a ground state neutral atom. Its electron configuration would be 1, because it's in the first row, so that's got principal energy level, and then S1. And so this 1 electron is going to go into the first energy level in the sublevel S, and it'll be the only electron there. Okay? Now let's go to helium. Helium has 2 electrons. Okay? We do not write, well, let's get to this in a second. Sorry. Helium is in the first row, so it's 1, and then it's over on the other end, S2. Okay? So the thing is, what I was about to say is, I know some people will write 1s1, 1s2. That is not correct, all right? Because first off, if I add up all the exponents, that's supposed to be all of the electrons, and now you're telling me there's 3 electrons, and that's not right, okay? So one of the rules for electron configuration is we don't write down we don't write anything down until we get to the end of a row, or we change blocks. So I'll write that down. we do not write anything down. We do not write until 1, end of a row, or 2, change sublevel blocks. Okay? So those are 2 little things to think about. So let's try this, go to the next one. Okay? Trying to make this as clear as possible, as much space. All right? Let's try lithium now. Lithium has 3 electrons. I start at the top. I don't start right at lithium. Again, there's different little ways you could do it, but I always like to start from the beginning. So I start at the very top. I don't see it. I go to the other side. I still don't see it. I finish a row. So I write the last thing down in that row. So that would be 1s2. Then I move to the second row, and there's my element, 2s1. All right? And that's my lithium atom. Okay? I'm going to jump a little bit. Let's try nitrogen. Nitrogen has 7 electrons. Start over again. I go across to helium. I finish a row. So I need to write down what finishes that row. Basically, I write that down. So 1s2. I come down. I'm back into 2s. But I'm going to leave it. Nitrogen's not in 2s, so I need to write the end of the end of the block right here, 2s2. Then I keep going and I finish. I'm in 2p3. Okay? And I'm sure it's okay. You might be like, wait, what? You know, let's keep going. I'm going to go all the way to calcium. Calcium. I go across, start the beginning, I finish the first row at helium, so 1s2. Basically, you always start with 1s2, okay? I move to the second row, I'm coming out of the s block, so I need to write 2s2. I go into the p block, I go all the way across, I finish it. So this is going to be 2p6. I come down, I'm now in the next row, so I go through that block. That's 3s2. Sorry for the bad writing there. All the way across the p, still no calcium, so this is 3p6. Then I finally get to the fourth row, and I end at Ca, which is 4s2. All right? And there's my electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. There are 20 electrons. I have figured out where every single electron is. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20. All right? Now, I stopped there because you can maybe already see some stuff right here, okay? As you get into the D block and everything. When you get into the D block, you can notice here that even though I'm on the fourth row, when I hit this first D block here, it's telling me to write 3D. And usually I tell the students to write 3D right at the edge there so they know what's going on. What turns out to happen is as I'm adding electrons in, when I hit the fourth energy level, I put 2 on in, and then it's lower energy. It's all about lower energy. Okay? That I can actually stuff 10 more electrons into what's called a D sublevel back on the third energy level. So what I like to say is the D block is always one behind the row. One behind the row. And you can see that going all the way down. I'm in the 5th row, but I'm in 4D. I'm in the 6th row, I'm in 5D. I'm in the 7th row, I'm in 6D. The thing you got to be careful with, though, is when you come out of the D block, when you come out at ZN, you're back up to 4P again. So the S and P blocks match the rows. The D block is one behind. So let's zoom on down and do one a little bit farther. I'm going to go ahead and say, let's do silver. Okay? I'm going to go pretty quick with this. I go across the top, 1s2. I go through the first 2 elements in 2s. It's not there, so 2s2. I go across 2p, so 2p6. I finish the row. 3s, I'm going to leave it. Go across 3p6. Then I'm into 4s, so that's 4s2. Now I go into 3D, and that's not where silver is, so I write 3D10. Then I come back out into 4P6 because I'm going to finish the row again. I go into 5S2, And then I finally reach silver, which is going to be 4d9. And that shows every electron located in the atom. All right? Last kind of crazy thing, and I know I just deleted all this stuff, but hopefully you've written some of it down. Okay, it just got too messy for me. All right? What about this bottom block down here? What the heck is happening here? Okay? So this is where it kind of is acting up a little bit. Okay? And again, this is showing the exception that we are not going to do. All right? So what you're going to run into some with this, okay? And again, I have my students kind of redraw it a little bit, okay? Is we're going to go ahead and put these first elements into basically 4F1 and 5F1, all right? And I know it's a little strange. This is showing because there's an exception where we actually put one electron into the D sublevel and then go to F. We are not doing that, so I am breaking the rules here, but this is what we follow in on-level and honors chemistry for the most part, okay? So, in that case, that's 4F1, so I should have put down here, this is 4F2, going all the way to 4F14, okay? And then lutetium is where we actually say 5D1. Again, that is not true, so I am breaking some rules here, but this is what we're going to go with to make it more simple for everybody. And again, if you go higher level in chemistry, you'll see that there are additional other rules that I'm not showing, okay? So, this is where the actual F block begins. And it makes some sense because that's lanthanum and that's actinium. So they are kind of starting the energy, the series at the bottom there, because we're going to learn they're called lanthanides and actinides, okay? So this is a funky. So the F block is 2 behind the row. The nice thing is there's only 2 F blocks, 2 behind row. And again, this is one of those things that we just kind of get used to. You use one that you have everything labeled very nicely, and then you obviously hopefully make the connections when you don't have it labeled anymore. But what would happen here, I'm going to go ahead and just do a big element. I'm going to go all the way to plutonium, 94. Okay? So it would be 1s2, first row, 2s2, 2s2, 2p6, 3s2, 3p6, 4s2. Where am I? I'm right here right now. 3d10, 4p6. 5s2, 4d10, 5p6. Where am I? I'm at xenon at the end here. So now I'm hitting the 6s. 6s2. I'm now headed down into the F block. The thing is, I'm going to go all the way across, so this will be 4f14. I have to then come back up to 5D, that's what this is trying to tell you, come back to 5D, 5D10, 6P6, 7S2, and then 5F1, 2, 3, 4, 5, 6. So that would be 5F6. There you go. That is your full electron configuration, all right? I will clearly not give you a ton of these problems on the test because they do take so long to go through, okay? But that is the process, and again, it's one you got to practice. I don't see many kids that are just like, boom, I got it, okay? It's something where you get the pattern. There is a clicking moment where it's like, oh, and then you see those people start moving through it very nicely, okay? So that is electron configuration. And I know we're just about to do some examples, okay? So I'm going to just kind of have these come on up. Lithium is 1s2, 2s1. Okay? Phosphorus, 1s2, 2s2, 2p6, 3s2, and then 3p3. Okay, there's a process with it. So we go back to the periodic table and do it. Chromium, I will actually go back just to show that one. Chromium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And that's what we got, so 3d4. So there you are. Okay? All right, last thing is orbital diagrams. Okay, orbital diagrams. So this is a little bit more visual showing of where the electrons all go. So an orbital diagram, okay, again, it's a visual showing of the electrons. This involves basically where you're going to draw the orbitals in correct energy levels and sublevels, okay, and then arrows representing the electrons. All right, that's what's basically being shown here. The arrows represent electrons, and we're going to be drawing them up and down to represent basically different spin directions. There's a rule that will explain that in a moment. So essentially what we have to do with this is we have to write out the electron configuration, and then we draw out how many boxes or orbitals there are in each of the sublevels, and we're going to fill them up with arrows. But there are a couple rules to follow here. We have what's called Pauli's exclusion principle. All right? There's only 2 electrons that can be in the same orbital, but they must have opposite spins. So you will see that we always have to draw one arrow up and one arrow down. Okay? So that's what we got there. Then we have what's called a Hund's rule. Hund's rule, electrons are always added to separate orbitals that have the same energy before you start pairing. Okay? So again, what that means, you'll see in a moment, is if I have 3 orbitals, I need to put 1 electron in each one first. Basically put, it's just like if you have multiple brothers and sisters. Everybody gets their own room until there's too many kids, and then we start having to pair them up. That's basically the idea. Okay? You have so many kids. I shouldn't say it's bad to have too many kids. Okay? So in P, D, and F sublevels, you add 1 electron to each box, each orbital with the same spin before going back and pairing each one with an opposite spin. Okay? So I know it's kind of weird. So again, here's the process. Write the electron configuration, spreading out each part a little. Based on the sublevel, draw the correct number of orbitals as short horizontal lines or small boxes. I like to do lines. And then draw the arrows based on the configuration. So what I do here, I'll go through these examples, is for carbon. Carbon is 1s2, 2s2, 2p2. It's okay if you're still kind of going, how are you getting that? Okay, I'm just going to show you now with how we do the orbital part. What I have to do is I look at the sublevel. So this is where we need to know the orbitals in each sublevel. If it's s, that's 1 sublevel, or sorry, 1 orbital. Okay, so 1s2 has 1 orbital, 2s2 has 1 orbital, s and s. P, the P sublevel, has 3 orbitals. So again, I like to do lines. What I then will do is basically using the exponent, it tells me how many electrons I should put on that line. If there's 2 and only 1 line, I need to put them opposite spins. 1 up, 1 down. That's Pauli's exclusion principle. 2s, 1 up, 1 down. In the last one, I have to follow Hund's rule. I have 3 orbitals, but only 2 electrons. So I do not want to pair them. That would be wrong. Okay? What I'm going to do is I basically draw 1 on one line and then 1 on the other line. And they're supposed to have the same spin. So if you mark 1 going down, that's actually incorrect. I'm going to keep on erasing that there. Okay? The other thing, though, too, is you need to draw the empty orbital. It's showing that there's still space for another electron to show up. But this one doesn't have it. Carbon doesn't have any more electrons. I am showing where every electron is clearly in the atom. So if I do argon, argon is 1s2, 2s2, 2p6, 3s2. I'm going to probably have to squeeze this a little bit, and then 3p6. So 1 orbital in each of the s's. I like to just draw each of those first, and then 3 in p. I see some people when they're trying to squeeze it where they kind of stack them like this. That's fine. But what I have here is there's full electrons in that orbital in 1s2. 2s2 is filled. 2p6. Technically, I'd fill 1 in each and then come back and start pairing. So that's actually following Hund's rule, but it's full. Then I move to the next energy level, 3s2. This is also showing you Offball's principle, where I always fill up 1s and then keep going. It turns out that argon it has completely full, oops, I want to draw it the right way. So you use that. 1 in each, and then pair. Okay? That is my electron configuration for argon. All right? So it's showing every single rule. Hund's rule, don't pair until you have to. Pauli's rule, opposite spin, off-ball, energy. That's the way I like to remember those. Last one is rhodium. Okay, I'm going to put this one up here. It's a little bit longer. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, yeah, I chose a long one here, 5s2, and then 4d, 1, 2, 3, 4, 5, 6, 7. Okay, so all the s's have 1, p's have 3, d has 5. And then basically you just draw a ton of arrows. 1. Now obviously when you're doing it, I mean in the end you're going to do probably this because you know it's filled, where you just draw them on in. You don't, clearly I'm not watching you fill them in, but that, again, the idea is we fill each one in separately and then pair them, but we know it's full. This 3D10 has 10 arrows, 10 electrons, 4p, 5s2, and then 4d7. So this one I do have to pay attention to. So 1, 2, 3, 4, 5, 6, 7. And that's how that would look. So that is how we can do orbital diagrams as well. Okay? So it's a lot. I am going to quickly try to go all the way back to that one off-ball diagram just to show you. I knew I was going to forget about it because I don't usually use this method, but some people really like it. The idea of this is if you draw out this diagram, okay, the idea is that you basically draw a line through the, and again, if you set it up appropriately, where you kind of line them up, okay, where you put 2p next to 2s, this is, if you're drawing a line, when you finish up one row, you go to the next one and it's telling you what you're filling up next. So that's why on this third row you fill up 2p and then 3s. Then you're going to do 3p and 4s. Then you do 3d, 4p, 5s. It's just another way to recognize how to fill up the electron configuration orbital diagrams correctly, showing Offball's principle. Okay, but I believe that's it. Just double checking now. Hey, yeah, we're all done. Okay, got the students all happy. Okay, so that's it. Okay, a pretty long video, but hopefully you'll find the pattern and you'll be good to go.